Every story has a beginning, even the story of the universe. Some 13.7 billion years ago, a mysterious event thrust the universe into motion in a big bang. The ultimate creation of every atom, every star, and every galaxy. But this is our story. How for thousands of years we've pieced together a vision of the universe, made sense of it through science, and discovered our place within it. This is our story of everything, from shaman to scientist, beyond the Big Bang. For thousands of years, we've gathered our observations of the heavens into books that would more than fill a library. We've built a vast body of knowledge about our universe. How it all began, how it will end. It's a work in progress. The script is still being written. The ink is still wet on the page. Where do we begin? Let's begin at the beginning. Let's begin with the Big Bang.
The Big Bang is a theory of cosmic evolution. It tells us how the universe evolved, how it changed from a split second after whatever brought it into existence, and we still don't know what that is until today.
When you look out at the universe and look at the other distant galaxies, you see that they're all fleeing away from us, that they're all moving outward at huge velocities. If you extrapolate that all the way back, you see that one time, maybe 13 or 14 billion years ago, everything that there was must have been compressed into one inconceivably dense point.
We know we don't have the whole story, but we've never had the whole story in the history of physics. We've had a series of better and better approximations revealing startlingly more and more beautiful and interesting truths.
The Big Bang is our theory for the beginning of the universe. But for a long time, people either didn't think about the origin of the universe, or they assumed the universe had always existed and was everlasting. Even scientists were reluctant at first to embrace the Big Bang.
It was meant to be a derisive term. However, the Big Bang is really a contradiction because it was not big and there was no bang. It wasn't big because we think that the universe started from a singularity of some sort, and there was no bang because there was no air to carry the vibrations. So a Big Bang is in some sense is a misnomer, but the name stuck.
And so has the theory.
Right now, I would say that the Big Bang theory is a solid part of science as we understand it. Anybody who doesn't accept it is regarded by most of the people in the community as essentially a crackpot.
But acceptance and understanding are two different things. The Big Bang theory doesn't yet provide all the answers science seeks to explain how our universe was born.
What cosmologists are referring to when they talk about the Big Bang theory is really only a description of the aftermath of the bang. The conventional Big Bang theory says nothing about what banged, why it banged, or what happened before it banged.
Right now, at this very second, we're in the aftermath of the Big Bang. Everything we see and hear and taste and smell and touch is the aftermath. The Big Bang is really our evolving, expanding universe. For us, mostly stuck on our rocky little planet, the view of the universe begins with Earth. This is Earth, silicon and oxygen-based, with a metallic core. The surface is mostly water. It teems with life and rotates once every 24 hours while orbiting a star called the Sun every 365 days. This is the Sun, mostly hydrogen and helium. Its surface temperature is nearly 10,000 degrees Fahrenheit. For energy, our Sun converts 700 million tons of hydrogen into 695 million tons of helium every second. The Sun is part of a solar system formed around 4.5 billion years ago that includes Earth and 7 other orbiting planets from Mercury to Neptune. And it isn't a stationary system. Our solar system is spinning, flying through space at 134 miles per second, turning in circles as part of a vast collection of stars and star systems. There may be 200 billion stars in this collection called the Milky Way galaxy. An estimated 6 billion of those stars with planetary systems like ours. Our solar system orbits the center of the Milky Way on one of its outer arms. The Milky Way is one of more than 125 billion galaxies that make up the visible universe. This is the universe. It's really, really big. And it's getting bigger. It's expanding. If the universe is expanding, then it used to be smaller. Much smaller. In fact, if we went back in time, we could watch it shrink. Back far enough, and the universe would be smaller than a galaxy. Back, and the universe is smaller than our solar system. Farther back, and everything that exists fits inside a stadium, a coffee cup, an atom. 13.7 billion years ago, the universe was smaller than the smallest part of an atom. Unbelievably small. Then, something happened. In a flash, everything suddenly expanded. This was how it all began. The first moment of existence. What we now call the Big Bang.
And that's what we know to be true, not because theorists have invented it, but because all the observations tell us. We can predict the abundance of light elements, and they agree over 10 orders of magnitude with what we see. So that fundamental picture that the universe is expanding and emerged out of a hot, dense universe, a finite time in the past, is the Big Bang picture.
During the latter days of the 20th century, scientists examined problems with the Big Bang, even though the theory was generally accepted. One of the biggest problems was that the temperature in outer space was strangely uniform. Physicists didn't expect that the universe would have the same temperature roughly everywhere they looked. The universe is simply too large for one end of it to be the same temperature as another. Yet it is.
It's the same thing that happens if you have a bathtub full of cold water and you pour in some hot water in one extreme. It's going to be a while before the whole bathtub has tepid water, because it takes time for that hot molecules to propagate across and normalize the whole distribution.
The universe doesn't appear to be old enough for its temperature to have equalized yet.
The Big Bang could not explain why such faraway points have the same temperature. In the early 80s, Alan Guth came up with this idea that perhaps the universe came from a very tiny volume. So tiny that within that volume, early on, there was time enough for these different points to communicate and normalize that temperature.
Right after this moment, Guth theorized that the universe expanded even faster than light. Faster than the cosmic speed limit, the ultimate speed, according to Einstein.
What inflation refers to is a theory of what propelled the expansion of the Big Bang.
Guth called his theory inflation. In the earliest moments of creation, for instance, scientists believe the four forces of nature, including gravity and electromagnetism, were actually combined into a single superforce. During the Big Bang, this superforce split into the four known forces. But before it split, when the universe was incredibly small, Einstein's laws of physics, including the one that says nothing moves faster than light, didn't apply yet. Maybe at that moment, something happened that caused the universe to expand even faster than light. So fast that it locked in the uniformity it had when the universe was still small.
We don't know exactly when inflation happened. Most likely it happened when gravity had split off from the other three forces, but at a time when the other three forces were still very likely unified.
This hyper-expansion, if it happened, would lock in a certain uniformity of temperature. Less than a billionth of a second after the Big Bang, a bubble much smaller than a fraction of an atom forms. This is the universe. It is unimaginably small and unimaginably hot. Within this bubble, the four known forces of nature, gravity, electromagnetism, plus the strong and the weak nuclear forces, are a combined superforce. Gravity suddenly splits off from the superforce as the universe expands. As the universe expands, it cools, which somehow sets off a burst of energy, fueling the hyperinflation of the universe, suggested by Alan Guth. This inflation locks in the uniformity of the universe pictured by the WMAP satellite. The universe is still less than a second old when the superforce decays into the separate forces of nature. Roughly 3 minutes after the Big Bang, the temperature of the universe has dropped to a mere 1 billion degrees Fahrenheit, cool enough for atomic nuclei to form. The element hydrogen forms. Some hydrogen atoms fuse to create helium, as proposed by Gamow and Alpher. 380,000 years later, and light travels through the darkness. The burst of radiation that Penzias and Wilson found happens now. 1 billion years after the Big Bang, stars take shape, producing the heavier elements like nitrogen, oxygen, and carbon, as Hoyle predicted. Roughly 9 billion years out, matter and gravity combine to form a perfectly typical star. Pressure creates heat at its core. This heat triggers thermonuclear fusion. A star is born. Stellar outflow clears away residual gases. A circumstellar disk of dust remains that eventually accrete into an entourage of planets and moons. One of these lumps of stardust, after being pummeled for eons by residual solar debris, has temperatures warm enough to allow hydrogen dioxide, water, to build up in the atmosphere. Liquid water gathers on the planet's surface. Underwater, mysterious chemical reactions ultimately form life. 13.7 billion years after the Big Bang, our universe is now 156 billion light years across. The sky is full of stars. Our solar system has 8 planets, more or less. The third planet is nearly covered in carbon-based life forms. Some are just realizing what infinitely small specks they are in the grand scheme of things.